like new um, devices and research. Yeah, welcome.
Yeah, thank you very much. Thank you for having me, and then thank you for have a chance to share all my experience related about this neural microstimulation and then programmable device development. And first of all, I don't know about our audience experience, but I briefly want to mention that neurostimulator primarily used for the restore the function of the function to people who are not unable to move, see, or hear, or modulate. Some certain functions are available, but it is not uh, easy to uh, easy to access or not control very well like a movement, for example, Parkinson disease and essential tremors like that. In this figure, you will see three primarily common applications for the deep brain stimulation and then other simulation applications. In the very left figure, you see the deep brain stimulation. Basically, the main idea is that there is a really long lead is reaching to subthalamic nucleus, and then some certain electrical pulses are delivering that region, and then it controls movement disorders. And the middle figure
One
is
example.
one
I
of
was
the applications.
exactly one centimeter. Sure.
So,
Yeah,
is
yeah,
there
yeah.
a problem?
Yeah, I think like there's like yeah, yeah. Please continue.
Okay. So in the middle figure, we will see the cochlear nucleus prosthesis. So in this common application, the idea is primarily bypassing the ear and then place all the microelectrode array to the like the sensory region in the midbrain, they call brain stem region, and then it stimulates the electrical stimulation pulses in there. And the very right figure is related about the spinal cord stimulation. It is mostly commonly used for the stroke patients or rehabilitation applications. So in our next slide, I just pressed. Sorry, it is okay. So in here you see the common neurostimulator system very closely. Neurostimulator is composing of two main components. One of them is IPG, we call it IPG, which is implantable pulse generator. Basically, there is electronics in there. You will see in the highlighted part, and there is also battery in there, either rechargeable or non-rechargeable battery. And then that part, IPG, generates electrical pulses. And there are electrodes. One of them is commonly used in we call as a Utah array. It is microelectrode array with multiple shanks. The other one is it's called leads, implantable leads. It has like a ring-shaped metal electrodes. It is also commonly used for the deep brain stimulations. Utah array called as a microelectrode arrays, and the leads are called as a macro electrodes. So in the right figure, it is also another application with the black rock neurotechnology. To basically, it's one of the impaired patients are sitting. If I remember correctly, he is ALS patient. So they basically implanted the microelectrode array to the brain region, and then the patient just imagination like a handwriting of some certain words, and then there is a decoder machine in the PC, and it decodes the neural signals, and then it generates a certain like words, letters with a meaningful manner. So in neurostimulation application is commonly used in broad range of diseases, such as epilepsy, migraine, pain control, also overactive bladder control and pelvic pain. These are the common applications in neurostimulations. And then these application is getting broad range through the time, and then because it is really effective, and then all this neurostimulation idea called as a bioelectronic medicine, and now this field is very popular in terms of the drug doesn't work in certain diseases. So there are 5 challenges for the neurostimulation applications. One of the first challenge is that the engineers, researchers design custom neurostimulators, but it composed of like multiple PCBs. It's a little bulky, size, shape, so it is not convenient to use like small animals such as rats or mouse. And the other second challenge is that like a tethering. You see, the rat is in a cage, and a cable is coming out from his brain, and this cabling is also affecting to neural signal quality and then efficiency, because the rat doesn't comfortable, so it affects all the study. The third challenge is that if we cannot control the charge injection amount, it causes like delamination on the microelectrode array. This is, you see on the right figure and at the bottom, you see all the lamination of the microelectrode array. So this is because of the excessive charge injection. The other causing problem of excessive charge injection is that we can also burn the tissues. So then that means whole study will be goes to trash. So the other one is on the last study, it's another application. We use microelectrode array for high charge injection capacity, but at the same time, we need to increase some certain limits. So in that case, we will do another technique to solve this problem, because because eventually our purpose is activate the nerves, but we hit like some certain limits for the charge injection capacity, but we need to solve this challenge to inject more charge. The other challenge is that like a traditional stimulation signal shape, like a certain period of pulses, sometimes doesn't work. So because of that, we need to change like a frequency modulation or amplitude modulation we need to do for especially like peripheral nerve stimulation, like you see on the figure. So these 5 challenges need to be solved for like ideal neurostimulation devices. So with this in mind, so I designed a neurostimulator system. System should be like more compact. Red can be carried on. It should be wirelessly controlled with a custom design interface, because there should be untethered connection. There should be electronic approach to solve the charge injection capacity problem. We call it the anodic bias applying voltage. And then also we should have a proposed like a voltage monitoring, like we will inject the charge injection signal through the electrodes, but at the same time we should monitor signal response. So we added all these features to solve all the 5 challenges. For that purposes, we have a microelectrode array. It is iridium based microelectrode array. You see we have 2 shanks, and each shank there are 2 different sizes microelectrode array. It's basically a rectangular shape electrodes. One of them is 2,000 micrometers square, and the other one is 4,000 micrometers square. So the advantage of microelectrode array is causing like less tissue injury, because it's like very straightforward. It's basically inserted the brain. So if the electrode size is bigger, it will cause more trauma on the brain. So the other advantage of the microelectrode array is that you can inject more charge to like a certain specific region, like a precision improvement. So in that purposes, we have a commonly used biphasic signal. It's called as a cathodic lead or anodic lead biphasic signals. So this should be like a charge balance. For example, on the figure A, it is symmetric and charge balance. In figure B, you will see asymmetric, but it's still charge balance. Charge balance, we can calculate charge or charge per phase. So basically, multiplying with the cathodic amplitude, multiply by cathodic pulse width, it will give us a charge amount per phase, and then that amount value should be exactly equal with the like another phase. Then if it doesn't like a match with the charge per phase, then there should be excessive charge will be happen, and this extra amount of charge will be stay on the tissue, and it will cause a like a physiological problem. So the idea is that it's just illustration. In here, we have basically working on counter electrode. We will drive the working electrode with the constant current stimulation signals, and at the constant current stimulation signal after injection, that at the electrode interface, the electrons will flow through the extracellular fluid and then reach out to the counter electrode, and then this circuit will complete with this two electrode combination. So in the like I said, the voltage monitoring is important after injecting the charge, because if there is an excessive charge is injected to the tissue, it will cause delamination on the microelectrode array or burning the tissues. So like you see, the blue figure is the voltage transient signals. VA is called as the ohmic drop, that it happens because of the electrode interface resistivity, basically. The like a curve shape, like a capacitive charge of the electrode, and then basically we will see a smooth transition, because the electrode surface is iridium, but it will be oxidized with oxide, and then there will be like another layer on top of the iridium, so it will be called iridium oxide. So because of that, there is a capacitive feature. Because of that, we will see this like a curve shape. So based on this examination of this blue signal shape, we will check the water window limit. For example, if for example, our electrode is iridium oxide. In the table, iridium oxide, the water window limit is between minus 0.6 volt to plus 0.8 volt. So if after injection the signal, if the voltage transient signal shape amplitude in this range, then that means we can safely inject the signal. If it is out of this range, that means we have started to damage to the microelectrode array. So for the, like I said, we use microelectrode array, but we need sometimes to increase the charge injection capacity, because eventual goal is to stimulate the nerves. So in this to solve this problem, engineer applications dividing by two main field. One of them is engineers like make the electrode surface area rather rough, and this roughness increase the surface area of the electrode. That helps the charge injection capacity. But for doing this type of modification on the microelectrode array, you need clean room activity to make a new electrode fabrication. Like you have to do all this process. And the other technique is applying anodic bias voltage. Basically, you apply some certain DC voltage, then you see the signal is shifted up a little bit. So, for example, in this case, it is around 0.3 volt applied bias voltage, and then we will see that our water window limit will be a little more safe with applying this voltage, then it means we can inject more charge. And the other techniques for the improve the simulation efficiency, there are two techniques: amplitude modulation and frequency modulation. In frequency modulation, amplitude modulated stimulation signals instead of constant amplitude stimulation signals cause a large ensemble of firing rate of neurons, such as cochlear implant application. We will see this type of shapes. In frequency modulation, frequency modulated stimulation signals decrease habituation to electrical current intensity in transcutaneous electrical nerve stimulation. So the other stimulation model is it's called the interleaved and then burst stimulation. So in the interleaved stimulation, you basically stimulate all the available stimulation channels. For example, in this graph, there are 16 channels, but the stimulation signals are not overlapped each other. For example, first channel begin and end in certain simulation period. Whenever it ends in certain time, second simulation channel starts. Same as for all the rest of the 16 channels. So the other technique is the burst stimulation. In burst stimulation, there is some certain stimulation period, but there is some pause. It calls as an interburst interval. So it basically in burst stimulation, we will mimic the firing rates of neurons. This is also commonly used for the pain management. So with all these ideas, with all these background concepts and challenges, we started our custom neurostimulator system. So we have three main components. One is computer, to control simulation parameters, to record all the voltage responses and all the get the results and see on the computer custom interface. And then our neurostimulator system basically generates our simulation signals and then derive all the simulation signals correctly. So with this, all the sketching and then all the theoretical knowledge, we will start with schematic design. And I use all designer PCB software, and I designed the schematic and created all the component libraries. And after that, you see the final PCB layout in here. So each colors represents each each layer. So basically, it has 6 signal layers and 4 power planes. So to make all the system as compact as possible with using discrete electronic components. And after we get all the PCB, you see on the bare or fabricated PCB on the left. So, and then we ordered all the components from some certain electronic distributor companies. And then we had all precise soldering station. It is a 1 mm tube size. In current technology, you can get like a all turnkey solution. Basically, you can submit all the fabrication files to the PCB companies. You just send what they call boom file, like a bill of materials file, and then they do all the assembly and they complete all the assembly and return back to you. But I prefer to do assembly manually because it was the first design. I don't know what will happen on the real circuit. So because of that, I assemble one by one, module by module. For example, I connected all the ground, I checked all the ground lines, power lines, and then make sure that there is no short circuit, there is no open circuit. And after that, I assembled like the power management part, and then I connected microcontroller part and some certain LEDs, and then I run the PCB to make sure that the code, like the firmware of the microcontroller, works properly. And after that, I was keep going to assemble rest of the components. So after assemble of the electronic components on the PCB, this is like a flow chart how the all the main functions are interconnecting with each other. On the left figure, you see the front view. It has a Bluetooth module, Bluetooth classical model, and it has also microcontroller, multiplexer, biphasic voltage generator. That means our stimulation signal generation part for the voltage signal shape, and then also evoke recording part for the recording the all the neural signals and filtering out there. In the backside, you will see all the voltage to current converter, like because we had to get like a constant current stimulation signals. So we have all these converters. Also, we have switches all the way on there because 16 switches control all 16 stimulation electrodes. So after all the electrical functions are done, I plan to like a firmware programming. So basically, in the firmware section, you have to set up all the clock settings, and then after that, you have to make all the peripheral settings for the UART communication, enabling to get all the data transfer through the Bluetooth. And then there are internal ADCs, like a built-in ADCs in the microcontroller to control like voltage transient recording, evoke recording, and battery monitoring signals. And then there are also multiple GPIOs to control switches and the multiplexers correctly. And then we have also, there are also SPI communication, like serial peripheral interface communication to control external 12-bit DAC. And then also we set, because we had to get like microsecond delay resolution for the pulse width. So because of that, I use certain timers to generate these signals. Then after the end of is all the programming, firmware programming and electrical tests and assemble of them. You will see the whole like a picture, like a rechargeable battery, microelectrode arrays already assembled to the omnetics multicolor cable. And this is the interface that I also designed in MATLAB App Designer to set like a Bluetooth communication control, like enable and disable easily, and set stimulation modes end user oriented, like it's easy to set which stimulation modes you want to stimulate the system, and also amplitude modulation, like frequency modulation and amplitude modulation, what should be the percentage rate, and then also stimulation parameter settings like an amplitude, pulse width, interface delay, frequency, and number of pulses. And then at the real time, you see the battery status and percentage rate. Yeah, it's basically you hit the run, and then the system send all the simulation and parameters to the system, and then you see like a real time the responses as a graph on the interface, and at the same time you see the file location. In these directories there are files, and then all the data will be storing as a CSV format. So yeah, like I mentioned that we use iridium oxide. That means activated iridium microelectrode array. Before activation, you see the figure A, the shape of the signal. This is you see like a metallic response of an array. But after activation of the iridium, you see like a bird shape CV measurements. That means we increase the charge storage capacity, and then also it is ready to use for the in vivo application. So, so we have a battery, we have a PCB, and then there, it will be nice to have like a canister. So I printed like a 3D printed ABS material use canister, like a place in easy to going out from the cable from certain, the gap. And then also I like assigned some certain pins for the battery charging. So I designed like a single tiny PCB and then assemble on the Omnetics connector. For example, the battery is, if it is battery is down, you just easily plug out the Omnetics colorful cable and then inserted the charging PCB and then just insert the general 110 volt electric outlet to charge the CD charging. To check the charge status, you easily see the like a real time on the user interface, whether make sure that battery charging is done or not. So in here, in figure A and figure B, like figure B is the magnified version of the figure A. In there, just simply there is a caged electronics and then microelectrode array immersed into the PBS solution. There is a counter electrode and it's connected in there with through a pin, and then our laptop has a custom interface. Just run the program and then see the simulation response as a validation before the animal studies. In animal studies, so we use male rat, like around 250 grams. So in figure A, B, C, it shows how the process is started and then like going on. So after following all the sterilization of all the tools, and then we shave the on top of the rat, and then fix on the stereotactic frame, and then cutting through the skin, and then on the lateral region, like medial lateral region, we made an opening, like a bone removal from that region, and then inserted a microelectrode array with carefully. Our counter electrode was a ball electrode shape electrode, so it was connected to the PCB ground. So this is like a little like a broad view of the how the in vivo study was applied during these studies. So in figure A, this is almost all you see that like a surgery table, like a microscope, and then also the rad is fixed on the stereotactic frame, and then all the electronics battery is on there. And then at the middle figure is a little bit zoom in version, like focusing on the electronics with the battery. And then in the figure B, you see the our laptop. There is no cable connection anywhere, just complete the wireless communication with the PCB on the rad. So after all this completed experimental setup, this is the like a system validation. So we basically enable like 5 different channels, channel 6 to 10, and we inserted, we drive with the 10 microamp custom current stimulation signals. This is the voltage transient response based on the electrode. So each electrode has some different responses. It is depending on the which tissue is interacting. We don't exactly know how the electrode interface in the brain with the electrode. So, and also some of the electrodes shapes are a little bigger than others. So because of that, we see even if we apply the same current, we will see the different voltage transient response. So that helps us that whether our stimulation signal is safe or not. For example, if you check the channel 10, is like a blue signal. So excuse me, channel 9 is a light blue signal. After injecting the 10 microamp, it is the voltage transients is less than 0.1 volt. That means channel 9 is safe to inject more current. But for example, channel 6, we see the voltage transient response is almost 1 volt. you see we don't focus on the ohmic drops like a sharp voltage. We don't focus on that. We just focus on the curve part. For the channel 6, it is around 1 volt. That means 10 microamp is too much for that electrode. So with this referencing of this voltage transient signals, we play with the other current amplitudes. In here, it is on a charge enhancement feature of our system. Uh, for charge enhancement, we use anodic bias voltage applying. For example, in figure A, we get a polarization voltage 174 millivolt with 10 microamp, but we need to increase more charge with the safely, and then we apply to the extra voltage, like DC voltage, and then in figure B you see the 0.5 volt apply DC voltage, and then you see that 100 microamp we can have 4 times more current we can apply, but cathodic polarization is still in the range like 310 millivolt. So that means that our charge enhancement features also works for this case. So also we tested inter-lead stimulation, whether it works or not for 5 different channels. Shall be overlapped or not, and then we see that it is safely inject multiple 5 channels without overlapping each other. So this is also other validation approach of intelligence, and this is also burst simulation idea. This is some certain 5 pulses, every 5 pulses per signal is driven, and then there is some certain pulse period between each burst signal. And then this is another validation of our stimulation signal system feature, which is frequency modulation. So initially, the stimulation signal frequency is low, and then we, in a linear mode, increase the frequency of the signal, and then see the response based on the adjustment on the user interface. And this is also amplitude modulation. Figure B is a 100% amplitude modulation, and figure A it is 33% amplitude modulation. We see that in the amplitude modulation frequency is the constant, just amplitude intensity is changed based on the percentage. And there are 3 different range: 33%, 66%, and 100%. So based on this range, a user easily set whatever prefers as an amplitude depth, and then the system successfully generates this amplitude modulated signal. So as a conclusion of this study, we overall we've solved all the 5 common challenges in the neurostimulation applications. So it is designed with discrete components. That means we can easily change some certain components, and then it is easily accessible, it is easily programmable, and then all the things in these studies custom designed, like PCB, user interface, canister, all of them are custom designed. That means we can easily play with based on the application. Yeah, thank you very much. This is all my study, and if you have any questions, just let me know.
Thank you. Thank you. Are there any audience have any questions? Okay. Someone asking. Okay, I will ask a few if to start up. What's the cost of this system? I think you mentioned it's low cost, but what exactly is the cost? For example, the PCB manufacturing is $200, something like that.
Yeah, it's $400.
$100?
No, 400, around $400 each PCB.
Each PCB takes 400. So what's the most expensive component in the setup? Like,
In this setup is on a microcontrollers is a little expensive, but PCB itself is expensive because it is 10 layer PCB and it's six signal layers for power planes. So in the PCB manufacturing, if you design like more layers, that means more expensive. So because of the PCB itself expensive, otherwise the components are cheap.
I see. Ah, so oh, I see. Okay. And then, and
Yeah,
then I see. And
let
then
me show you
how many layers do you have in the PCB, like for this design?
the 10 layers.
Oh, you have 10 layers? That's
Yeah,
quite a lot, right? Like compared to what, like the usual, like
exactly. For example, in like simple applications, people make let's see here, sorry, two layers or single layer, and then if this circuit is designed with single layer, that means it maybe the size will be 4 times or 5 times bigger. So our idea is like a shrinking as much as possible. And because of that, the size constraint, because we will have to use only small animals, so it has to be well, because of that it has to be small. Because of that, yeah, it is complex, expensive. Yeah,
I see, I see. So that's I see. Yeah, I see. Oh yeah, I see. That's why it's quite different from all other electronic stuff in like which like they
exactly.
usually do like two design. Like it's very dense, like the design that you
Yeah,
have here. It's going
exactly. Super nice. Yeah.
is that going to cause like instability like when you have like 10 layers? Like
Sorry, question again.
I mean like it's like if you have like so many layers, is this going to cause like instabilities? For example, if you
Oh,
run
I see.
like one day or something like that.
Oh, no, this I follow up all the they call AMI, EMC rules, like a shielding and all the things. So I follow up all the rules for like try to avoid like a crosstalk happening because in the PCB design there are challenges like a crosstalk. That means if the traces are really close to each other and then the signals are interfering with each other. So yeah, I follow up all the rules and then that was there was no stability issue because for example I tested the system with driving 4 million cycles. You could set 4 million number of pulses, and I run the system to make sure that the system is correctly derive electrode arrays without interrupting. So it worked very well.
I see. Okay, that's great. Like that's very interesting. Yeah. Um,
Mhm. Okay. This is common approach, like in after designing this type of electronics or things, people make calculate how many how many million cycles it will be enough to test the system. And then you program it, and then you leave it the system and run it.
I see. What microcontrollers are you using?
STM32. It is a ARM Cortex M7 microcontroller.
I see. Oh, I was thinking there are some like cheaper like Chinese versions like that you can use, right? Like they sell pretty cheap ones. Yeah.
Yeah. Yeah, STM32 has nice IDE, and then also the documentation and all the things are uh, like super there are lots of users are in the world using. So because of that, you know, documentation is key in the microcontroller, like reference manuals. So STM32 is really powerful in that. But yeah, there are lots of microcontrollers in the market. I'm sure Chinese and other versions also work.
I see. Yeah. Anyone have any other questions? Great. I think the audience are pretty satisfied. Yeah. So thank you for being here. I think I will stop the recording. Let me